Hello, everyone. Let's start today's lecture. Please turn on your camera. Okay, so in the last lecture, we learned about how to train a neural network. Today, we are going to continue our discussion about that. Before we start, let's go to review some important things we covered in the last lecture. So let me ask question 2. Let me see. Konstantin Shusuke?
Yes.
Right here. It's a right pronunciation.
Konstantin, yes.
Yes. Okay, so in the last lecture, we learned about pooling layer. So let me ask a question with some details. So we have an image of 32 by 32 with 3 channels RGB code. And if we apply 2 by 2 max pooling with stride size 2, then what is the number of parameters we are going to learn?
2 by 2.
2 by 2
Wait.
max here with stride size 2.
32 by 32 and 2 by 2 max pooling with stride by size 2.
Yeah.
Then we have 15 by 15 by 15.
Why is that?
Because with the size we have no padding, so we miss the edges in a way, and then with the stride size 2 we only take a step of 2, so only half as many as we had as input.
I think you are answering the output size, but what I'm asking is the number of parameters that we are going to learn.
Oh, none, because the pooling layer has no parameters.
Okay, yeah. So yeah, the correct answer is 0. Good job. And the output size is actually 16 by 16 because it's 32 by 32, and each 2 by 2 patch is pooled to one single value. So the size will be exactly the half. Okay, let's move on to the next one. Let me see. Akison, Jonathan.
Yes.
Yeah, your name is too long in this system. So
Jonathan.
Jonathan. Okay. Yeah. So in the last lecture, we learned that the sigmoid function has a lot of drawbacks. So can you do you remember what were they?
Yeah, I think so. It was that it killed the gradient for big numbers. And it's only positive numbers. It's not zero-centered. And also that it uses the x function that is somewhat, yeah, it takes a longer time.
Yeah, that's great. That's perfect answer. So he answered 3 things. Sigmoid function kills the gradients, which was the most serious problem with sigmoid function as the activation. And also it outputs non-zero-centered values. And also as a minor effect, exponential function is quite expensive to compute. So yeah, great job. You know that. Okay, and the next question. Let me ask this to Ren Wang.
Yeah, Professor, can you hear me?
Yeah. Yes. Yeah, we learned about ReLU, or rectified linear units activation function, but it also has some issues. Do you remember what was the drawback of ReLU?
I think it's the that gradient problem of if the input value of ReLU function is negative, then the gradient will be 0. So we can't do anything for this part. That's the problem.
Yeah, good job. Yeah, that problem is called dead value. So if the initial input is negative, then the gradient will be 0, and it will not be updated. In the next example, it will be also, again, negative because it wasn't updated, and that will be just continuing. So those neuron will be just killed and will not be updated at all. So this was a problem. So we recommended to initialize it with some slightly positive numbers, which we are going to see in today's lecture as well. Great job. Okay, and the next question, Yerim, Kim Yerim.
Yes.
Yeah, we learned about principal component analysis. Can you explain what it is?
PCA is for just reducing the dimensionality of the data.
Yes, how?
By calculating the largest variance of the data and change the axis of them.
Mm-hmm. Okay, great. Yeah, as she said, PCA is some dimension reduction technique that we can reduce the high dimensional data into smaller dimensions, and the method actually tries to find the direction with the largest variance, and we set that as the first principal components, and among the remaining dimensions, we find the next second largest variance direction, and we keep that as a second principal components, and we just keep doing that, but we have to maintain all of those chosen axes to be orthogonal to each other. So in that way, we actually try to preserve the variance or the amount of information as much as possible while we are reducing the dimensionality. So, okay, that's a good answer. The last question is about data augmentation. So let's ask this to Jiwon, Kang Jiwon.
Yes, Professor.
Yeah, why do we do the data augmentation and what it is?
To make the data set bigger, to grow, and add kind of various variety into the data set. Because the data set might not represent all the possible images in the real world.
Yeah, I was waiting for that last sentence, so thanks for that. So the images are, even though we have very big data, still it just captures one moment in the pixel-wise canvas. Actually, that's just a one very specific image that we can think of, even though for human it looks very similar, but in the pixel-wise there can be a lot of variations. So for example, we can reflect horizontal reflection or the vertical reflection, or we can also do some change of the colors, tones, or we can be very creative to make actually take advantage of the same image to create something similar, but pixel-wise completely different, but the semantics still is the same. So that is the main motivation for data augmentation. And in computer vision, I said that it's really common and it's really important because the images are not reflecting all the pixel-wise variations that we can think of in our input dimensions. So today, yeah, I'm really satisfied. Most students answered really well. So yeah, please keep going, keep doing this in the rest of this class. Great. So today, we're going to finish the lecture 6 with the last topic, weight initialization, and we're going to continue this discussion about how should we train our neural networks more effectively. So how should we initialize the initial parameter values of these neural networks, even though we are going to use stochastic gradient descent or something else to update those parameter values to fit our data? But how should we initiate that? We just discussed that this as a kind of randomly. We can just start any values and it's okay. We can just update that later. But does it really matter what initial values should be? So previously, before the deep learning era, the neural network was introduced quite a long time ago in 1970s or something, 60s or 70s. At that time, the network was much shallower because we didn't have that much big data. So what people usually used was standard normal distribution, which is the zero mean and some standard deviation, some small standard deviation to give some small variations in the initial values, but it was zero-centered and it's just small constant. So it was widely used and it was okay in traditional shallow neural networks, but that became problematic as we have larger data set and we stack a lot of layers to make the models deeper. So let's see here. Suppose we have 7 layers of this size, and the input is just 16-dimensional vector called x. And we are going to create 7 layers of this size, with which is called W here. So if you're not familiar with the notation here in Python, this is the dimensions are these things. And from the first until the second last, and this is from the second to the last. So in the first iteration of this loop, this is from the very first to the second, and the next one is the second to third. So each layers are connected by these weights W. And W is initialized by some random values. This is random normal, so some normal distribution with 0.01 as a standard deviation. So this looks okay, but what problem do we have with a deeper network? Let's see this. Suppose we are using hyperbolic tangent activation function, which looks like this, which is zero mean, as we discussed last time. So if we give the input of these small numbers, at the very beginning, it's okay. It outputs very nice distribution between -1 to 1. And most of them are centered on 0, and nothing is above 1 or below -1 because we are using hyperbolic tangent. But output of this is centered at 0 because we are multiplying 0.01 here. So the output gets smaller compared to its input. In the second layer, because the input was smaller, the output gets even smaller. Third layer, it gets even smaller again and again and again. We have 6 layers here, but in modern neural networks, in deep learning, they are like 50 or 100 or 300 or something like that. So it's the initial values will be just converging to 0 if we have too many layers. And what is the problem with that? Suppose we are updating these weights, and we can compute the partial gradients of hyperbolic tangent with its input with regards to the weight values. Then it will look like this. So itself and multiplied by, because we are taking the partial derivative with W, we need to multiply with X. And because this X is very small number here, the gradient will get smaller very quickly. So because this input is close to 0, all gradients will be also close to 0. So no learning happens, which is a bad thing. We just initialized with very small numbers, and just because of that, model learns nothing. So what should be the remedy? Okay, so it seems it's a problem because the input is the initial values is too small. So just make it bigger. So instead of 0.01, we changed it to 0.5, 50 times larger. Then what happens? Okay, now it's too large. So our output will be either 1 or -1 for most cases. And because they are saturated like that, in the second layer, they will also output, because most of these inputs are 1 or -1, the output is still 1 or -1. So it's polarized from the beginning until the end like this, which is also a problem. Because if we compute the gradients here, we do exactly the same thing as before. The tangent hyperbolic its gradient is computed like that, and we have to multiply x here. And if this is almost 1, then the first part will be 1 minus 1, so it's close to 0. So again, it learns nothing. So to conclude, if the initial values are too small, that's a problem. We learn nothing. If it's too large, we also learn nothing. So it gives some ideas that we have to be careful to initialize to something between these two extremes. But what are these proper intermediate okay values? 0.01 is too small, 0.5 is too large. How should we know that? So what people found out is we can actually initialize and divide by the square root of the input size. How do they know that? So it's named after its inventor, Javier. So it's called Javier initialization. So we need the just right scale where the activations are nicely scaled for all layers. So if we do this, just showing how it works. So in the input layer, it's a little bit polarized, but it's well distributed. And in the later layers, it's slightly getting into the 0, but it's still, even at the last layer, very last layer, it's actually well distributed around 0 and between -1 and 1. Here, the number of input dimensions is the number of parameters that we are going to learn. So in the fully connected, it's the number of edges. And in the conv layers, we have computed this before. It's the number of filters, the values in the filter times the number of channels. Strictly speaking, we usually have one more, the bias term, but that doesn't affect a lot because we are just estimating the right scale here. So yeah, if you're uncomfortable with that, you can add +1 here. But, so why does this work? Let me briefly explain how does that, how do they found out that this is the right scale with some maths. So if you, please try to follow me, and if you cannot understand within this lecture, please review this materials. I try to be as much as complete in these slides. This was added this year. Last year I was whiteboarding, but it wasn't work really well. So let's start this. The output is computed as linear multiplication of the weights and the input for each layer. And let's call that x is the input with some vector of dimensionality of d in. This is the input dimensionality for each layer. And output is the out size vector. So the W should be the size of, it's a matrix of size d out times d in, as we discussed before. Then each element of y is computed as this matrix vector multiplication. So each element of yi is, this is vector, ith row vector, and x is a vector. So they are taking inner product. Or element-wise, we can see, write like this. So wij and xj are multiplied and summed for all the elements in the input dimension size. So far, so good. Okay. So let's think about its variance. What should be the right variance size of these input W values, the weight, initial weight values of these Ws? So let's think about the variance of this. So taking the variance on the right. So that's given here. And I rewrote that here. So the variance of yi is given as this. And here we take some assumptions. So if two random variables are independent to each other, variance of those, some of those random variables are actually sum of the variance of each random variables, only if they are independent. Here, the x is data, and w is any random values. So actually, this is a valid assumption. They are independent, right? So we can write like this. The variance can go inside of this summation using this characteristics. And then we take another assumption that if w and x, two random variables, are identically distributed, which means we are talking about these J's. WI1 and WI2, these are the weight values for each dimensionality of the features or the inputs, right? They are independent to each other because when we initialize them, we don't care about the other values, but we just randomly initialize each of those dimensions. Dimensionality in the input are usually not independent, but we just assume that they are independent. It depends on the data, but usually it's not independent. So when you combine these independent and identically distributed, it is called IID. You're going to see this many times if you study machine learning. Independent and identically distributed, they are, strictly speaking, usually not valid, but in a lot of machine learning models, they actually assume that the given data is IID. So it's kind of common assumption. So if we do this, then the variance of yi can be expressed like this. din is multiplied with each of these variants. And yeah, we can write like this. Then, using the definition of variance, which is this, you learned this in high school, right? We can re-express this using expectation instead of the variance, which can be written as this, right? This is just direct application of this. And then we're going to make another assumption that actually this is the same assumption as this. W and X are independent, right? We assume that, and that's usually true. The weights and the data itself is not dependent on each other, especially at the beginning. So using the characteristics, the properties of the expectation of independent random variables, the expectation can be just multiplied if they are independent. So using this properties, we can just split these expectations between two random variables to this. And here inside of this can be split like that, and we can take the squares here. Okay? So then this is our current formula. Then we assume these things. So when we initialize the W, we are using the normal distribution with zero mean. So expectation of W is 0. This is not just assumption, we just use it. So this is true in our model. Expectation of X, the input data, is usually not 0, but we know that we can make it by data pre-processing, as we discussed in the last lecture. So we can make this valid by data pre-processing. Then we use this, but because the expectation of X is 0, this part is gone. So variance of X is equal to expectation of X squares. So the right term here will be disappearing because both of these are 0. And here, the squared expectation is same as its variance. So that's how we get this here, okay? The variance of yi is multiplication of these three under all of these kind of valid assumptions. Then, if we set this variance of wij, this is what we would like to set here. Remember, we are initializing the weight values to some normal distribution with some variance, and we would like to set that variance. So variance of this W, if we set this as 1 divided by the input dimensionality, then this will cancel out, right? D in times variance of W, this will cancel out if we set this as 1 divided by D in. So then variance of yi will be same as variance of xj, which is output variance is same as input variance. That's what we want, right? For every layer, we would like to keep the variance as same. Otherwise, it will shrink or explode. So that's just roughly, we can keep the variance at the same level by setting the variance of W as this, 1 divided by input size. So that's how, this is just brief explanation of how this setting actually works. again, if you are not following this, please review this. And if you can still don't understand, please ask me a question. So far we saw the case of the hyperbolic tangent, but in the last lecture I told that let's not to use it. But, so what about ReLU? What happens here? So ReLU looks like this, and the activation is 0 if the input is negative, and if it's positive, then the X is just output as is. So if the weight is too small, the same thing happens. The input is small and output is still same, but it's still small. Then in the next layer, it's getting smaller and smaller. So in the beginning, all of these zeros are probably from the negative inputs, but the positive inputs are at the beginning distributed between 0 and 1 kind of uniformly. But later, they get smaller and smaller, and they are kind of concentrating to 0, which is not a good thing. So if X is close to 0, then all gradients are still close to 0, and the learning is slower. It's not as dramatic as the previous example with the hyperbolic tangent, but still, it's not ideal. So I'm not going to go to the details here, but researchers try to do the similar things as we discussed before. So they found out that dividing by the square root of the 2 divided by input size, then it's working like this. It's quite change. The distribution doesn't change after layer by layer. So the principle is the same. We need to be in just the right scale where the activations are not affecting the variance of the input distribution. So if you are interested in these kind of things, these are still proper initialization is an active area of research, and there are a lot of recent papers that discusses the effects of initialization. So if you're interested in this line of research, please follow these papers. And yeah, that's the end of the lecture 6. Before we move on, do you have any questions?